Okay guys, so here's phase 6. So I'm going to do a couple examples sketching a solution curve on a slope field. So here we're given a slope field. The slope field from a certain differential equation is shown above. Which of the following could be a specific solution to that differential equation? So these down here, these are not differential equations. They are potential solutions to the differential equation that generated this slope field. And the way that you see the solution curve within a slope field is like this. So pretend that the slope field like represents a weather pattern or like a storm pattern or something. And the way that the slopes are cut is telling you like the direction that, the pattern is taking the air in or whatever. So, but let's take this point. Let's pretend this point is dropped here on the weather pattern. How is it going to travel over time according to the way that the slopes are? It'd be traveling like this. You just follow the path of the slopes. Like if it dropped me right here, I'd be going like that. Okay, so I want to draw let's say that we were dropped right there in the weather pattern, and then following the slopes, it would be like this. That is not the graph of x squared. That is not the graph of e to the x, nor e to the negative x. Definitely not the graph of cosine. That is the most similar to the graph of natural log of x, okay? And guys, you just kind of have to know what these look like. X squared, looks like that. E to the x, that's an exponential function. It looks like that. E to the negative x would just flip it over the y-axis. And then cosine is like that. Okay. Yes, next one. Same idea. The slope field for a certain differential equation is shown above. Which of the following could be a specific solution to that differential equation? Imagine this is a weather pattern. Drop a point anywhere. How is the pattern going to take the point? It would go like, these slopes would be going up like that. And then down like that. So like, all right, that should look familiar as a cubic. All right, it's not sine, it's not cosine, it's not x squared, it's not natural log of x. That is a cubic function. All right, let's do one more. So sometimes they're going to tell you where the point should be dropped. So the calculator drawn slope field for the differential equation here is shown in the figure above. Sketch the solution curve through the point 0, 1. So here's the point 0, 1. It's like right there. Now to the left, the slopes would be carrying the point like up like that. And then to the right, they'd be carrying it like, how would they be carrying it? Like this kind of, well guys, anytime you see like a straight line of equal slopes, if you were to be dropped right on that line, you would just be carried along that line. But if you were to be dropped on either side of that line, what that line is an asymptote, okay? So yeah, if I'm dropped on 0, 1, my graph's gonna be looking something like that. Then they want me to drop such the solution curve through this point, -3, 0. So if I were dropped on -3, 0, the slopes would be taking me like that along the asymptote and then down there. So I'm sketching. So 0, 1, I'll sketch like that. And I just need to know that's an asymptote. And then that one. Okay, so you just follow the pattern. Now, so those were just gearing up for this pre-response problem. So consider the differential equation right there. A slope field for the given differential equation is shown below. Sketch the solution curve that passes through the point 0, 2, and sketch the solution curve that passes through the point 1, 0. Okay, so through 0, 2, remember what I said, if you're dropped right on a line, then the pattern is going to have you stay on that line. So through 0, 2, this is the graph. Guys, they're gonna look for you, you know, starting at the right point, following the path of the slopes, and then they want to see that it is drawn to the end of the grid. All right, so that's the one for 0, 2. Now the one for 1, 0. Okay, so 1, 0 is here. All right, if I follow the slopes to the right, I'm going to be going like that. Now if I follow the slopes to the left, I'm going to follow them like down, down, down. Then they go like, you know, horizontal, something like that. And you could see the symmetry. Okay, this is like there's symmetry here, so this should look like relatively symmetric. There we go. Okay, so full credit right there on that part. Now, let y equals f of x be the particular solution to the given differential equation with the initial condition f of 1 equals 0. All right, so here they're telling you that 1, 0 is a point on the original y equals f of x. Write an equation for the tangent line to the graph y equals f of x at x equals 1. Use your equation to approximate f of 0.7. So you need to know this formula, y equals f of a plus f prime of a, x minus a. That's the equation of a tangent line. And in this case, we're plugging in f of 1. Okay, now f of 1 is 0. We know that from here. F prime of 1, I've got to do a little aside. So dy dx evaluated at 1, 0, it equals, so I'm just plugging 1 and 0 into there. So 1 is going in for x, and then 0 is going in for y. This ends up being 4/3 plus 4/3, x minus 1. Okay, so y equals 4/3 x minus 1. So that's part of it. Write the equation for the tangent line. Then use your equation to approximate f of 0.7. Now guys, so this is like the equation of the tangent line, but then remember, sometimes we use this notation for linear approximation. All right. All right, so that's the linear approximation. So I'm just going to plug in 0.7 into the linear approximation. Okay. Guys, this is negative 0.3 right there. This is a no calculator section. And, you know, you could do this differently than me, but I like to convert to fractions. So this ends up being negative 4/10, negative 2/5. You don't even need to simplify though. So f of 0.7 is approximately negative 2/5. Okay. Now, the last part. Find the particular solution, y equals f of x, to the given differential equation with initial condition f of 1 equals 0. Guys, if they are stating it like this means solve for y. That's what that means. Okay, because that's how they want the solution expressed. All right, so let me grab an extra piece of paper. Okay, right here. All right, so this is going to be part C. All right, so the algebra might be a little bit heavy, so, you know, pay careful attention. If you feel like you can't do some of the algebra, like if you're like, oh, I wouldn't be able to do that, then practice going through those exact same motions on your own. And you could even ask me for extra practice similar to like the algebra that I'm about to do. All right, so this is the differential equation. I got to separate the variables. Okay, so y is over there, x is over there. So you could start by cross multiplying if you want. Okay, this y minus 2 squared I need over there. dy. Okay, now I need to take the antiderivative, but I notice immediately, guys, that this is going to be tricky over here. I'm probably going to need u substitution, and because this is a binomial squared, if I represent it with a negative exponent like that, I'll be able to use power rule eventually. All right, then you do the antiderivative. So here I'm going to need u substitution. So u is y minus 2. So du is just 1 dy. Okay, so the integral u to the negative 2 dy, 1/3 x dx. Okay, if you like parentheses, I used to do them all the time. You could even put them there. Now antiderivatives. So this is going to be u to the negative 1, and then you're dividing by negative 1, so that'll be negative. This is 1/3 x squared, but then you divide by 2. That'd be a half, so that'd be a 6. Plus c, don't forget that. Now I'll plug the u back in. With definite integrals, when there's numbers on the end, you don't plug the u back in because you turn the endpoints into u values also. And then when you use the fundamental theorem, that's the thing with the brackets and the, plugging in the numbers into the antiderivative and subtracting. When since these would be u values, you'd never have to plug the u back in. But with an indefinite integral, which simply means antiderivative, you've got to plug the u back in. So this is negative y minus 2 to the negative 1 is a 6th x squared plus c. Now we got to find c by using the initial condition. So we know that they want this initial condition, f of 1 equals 0. So f of 1 equals 0. That means we've got 1, 0 is a point on this. So in for y is going 0. So that's negative 2 to the negative 1. And for x is going 1. Okay, this ends up being negative a half right there. And if that doesn't make sense to you, please think about it. So that just ends up being positive a half. And then you solve for c. So I'll make this 3/6. So you get c is 2/6. C is a third. If any of that doesn't make sense, make sure you think about it. It needs to make sense. Okay, so we're almost done. We've almost got all the credit. We've just got to solve for y. And you might be like, oh my gosh, how do I do that? Well, first, let's make things fractions. Okay, so this is negative 1 over y minus 2 equals 1/6 x squared plus a third. Now, guys, kind of a messy way. Let me do it a nice, clean looking way, and then I'll show you like a messy way that would also work. So here I've got just like this single fraction. If I make this a single fraction, then I could cross multiply. That might help. So I could multiply this by 2 over 2. So this is negative 1, y minus 2 is x squared plus 2 over 6. All right. Then if you want, you can cross multiply. So that'd be negative 6 equals x plus 2 times y minus 2. Now I want to get the y's by itself, so I'll divide both sides by this binomial. So y minus 2 is negative 6 over x squared plus 2, and then I just add 2. Y equals negative 6. Okay. Now, from here, all right, let me just say or, and then I'll block this off. Okay, or you could cross multiply like at the beginning. So that you could be like -1 equals 1/6 x squared plus a third, group that, times y minus 2. And then y minus 2 is -1 over 1/6 x squared plus a third. So y is -1, 1/6 x squared plus a third plus 2. This is a messier version. Works too, but it works also. As long as y is solved for, it doesn't matter how simplified the final answer is. All right, so I'll just say here alternative. Alternative. All right, so if that speaks to you more, you know, that's up to you to use. Okay. Yeah, so that's it.